All right, so let's see if I can go through this. What I was going to go through this morning, and obviously had severe technical issues. I wasn't able to stay on Zoom for longer than a minute. So we're going to do, this will be the first of two parts of doing area of a triangle. And of course, I'm sure you remember from geometry class that when you do area of a triangle, you can just do 1/2 base times height, and you're able to use any of the three sides as your base. So let's just say I have this base here, but if you want the height, you have to go from the opposite vertex and then perpendicular to that other side. So that's the height. Okay, so from our perspective, we're going to talk about how we can figure out what that height is from a from a trigonometric perspective. So remember that our formula for the area of a triangle is 1/2 base times height. But let's see if we can focus on a different way to figure out this height rather than worried necessarily about what the length of that side is. I mean, we're going to calculate it, but what I mean is in the formula, we won't actually have the letter H in there. We'll have something else in there. All right, well, let's say this side A. Then this angle would be gamma. That's the one in between them, because this would have to be angle C, if you will, with the little c over on the other side. All right, so if I know A and I know B, and I know the angle between them, I can actually figure out what the length of this side is. And it doesn't matter what B is, actually. Because notice for gamma, the opposite side is H, the hypotenuse is A. So I know that the sine of gamma in this scenario is H over A, or H is equal to A sine of gamma. So now I have H in terms of information that I know, A and gamma. So when I go into the area formula, I get 1/2 AB sine of gamma. So this is the area formula that we're going to use. Notice that there is nothing special about A or B or gamma here, except that gamma is the included angle between A and B. So I could have also written this formula as 1/2 BC sine of alpha, because alpha would be the angle in between B and C. We could have also written it as 1/2 AC sine of beta, because beta is included between A and C. The moral of the story is it's two sides and the included angle. So that's what we have to have. If we have that, we can figure out the area of the triangle. Okay, so let's do a problem. Let's look at this triangle where we've got AC here has length 8, BC here has length 11, and angle C has measure 113. So I have two sides in the included angle. So this would be the area would be 1/2. This over here is side A. This over here is side B. This would be gamma, because it's angle C. So that actually fits that first version of the formula. But again, I'm not as worried about the actual letters that are in the formula as opposed to knowing that you need two sides and the included angle. Can't be an opposite angle. It has to be an included angle, right? It has to be the one that's in between the two sides. Okay. Exactly the setup we have here, though. A is 11. B is 8. And the gamma is 113. And this, again, looks like an awesome job for a calculator, and I'm not going to spend the time switching back and forth between screens. I figure at this point, you should be able to type these into your calculator without too much difficulty. And we get that the area is 40.5022. This will be centimeters squared. Area is always given to you in square units, and we can see why, because this A has a centimeter attached to it, and this B has a centimeters attached to it, which means when you multiply A and B together, you get a centimeters squared for the units. Okay, so that would be the area of that triangle. Scroll over here to number 2. All right, so these are different letters, but again, the setup looks exactly the same as the previous one. I have two sides, 9.9 and 15, and I have the angle included between those two sides, that's 72. That's important, okay? If this 72 were down here, I wouldn't be able to do this problem right off. I'd have to do something else first, which we'll see examples of that here in a little bit. The 72 being the included angle is the important part. All right, so the formula again is 1/2 A, B, sine of gamma, or whatever combination of letters you want. But again, remembering two sides included angle, which is what we have. So this is 1/2. I can use 9.9 for my A, 15 for my B, and 72 degrees for my gamma. I do 0.5 times 9.9 times 15 times sine of 72. Again, looks like a wonderful job for a calculator. 70.6159. Now the units here, I'm doing feet times feet, so I get square feet. All right. So again, it's a straightforward process of doing this once we have the two sides and the included angle. Okay. So let's look at this problem where we have to do a little bit more work before we can get to the point of being able to figuring out the area. All right, so this problem gives you that we have a side that's 11 and an angle that's 71.45. They don't tell us any other information except that the PQ and the QR, these two, or excuse me, PQ and PR, are the same size. They're the same length. It's an isosceles triangle. They ask us to find the area. Well, the isosceles triangle bit tells us a little bit of information. This tells us that this angle here has to be also 71.45 degrees because the base angles of an isosceles triangle, these would be the base angles, have to be the same length. Which also tells us that we can figure out this angle. If I want to know what the measure of angle P is here, I know that they all have to add up to 180, so I would do 180 minus 71.45 minus 71.45. That's 142.9. So that would give you what? 7.1? No. 37.1. Right? Because if I do add that to 142.9, you should get 37.1. Right, let's just make sure that's right. So 142.9 plus 37.1 really gives us 180. Yep. Okay. Cool. Wonderful. Now I know all the angles. So really, all I need to know is one more side, and then I'm done. We can figure out what the area is. I just need one more side. I don't need both sides. I mean, once I figure out one, I know the other, but I just need one more side because I just need two sides in the included angle. So now we can use our law of sines to figure out, let's say this is, I'm just going to give it a little letter Q since it's opposite angle Q. Sine 71.45 over Q has to be sine of 37.1 over 11, right? That's our law of sines, right? Angle, sine of the angle over the opposite side, sine of the angle over the opposite side. So Q here will be 11 sine of 74.45 over sine of 37.1. And if we type all that into the calculator again, let's see what we get. And divided by sine of 37.1, we get 17.2884. Which means the other side is also the 17.2884, but now we can use our law. Now we have two sides and the included angle, so the area will be 1/2 times 11, that's one side, times the 17.2884, that's this side, the Q side, times the sine of the 71.45. So put that into our calculator. And we get sine 0.45. We get 90.1462. And I know it says around to the nearest tenth, but I'm not really worried about that direction here when I'm just trying to illustrate the problem. You should also probably note that I could have also used this for this side as well. And you could have done the area is equal to 1/2 the 17.2884 times itself times the sine of 37.1 degrees. That would have been a perfectly good way to solve the problem, and you should get the exact same number. So you could go type this into your calculator and make sure that you really do get the same value as we got before. And if we've done everything right, we should. All right, let's do another example here. So this one, just draw the picture. I'm not going to draw it to scale because that really doesn't matter when doing these problems, just trying to solve them. I know my alpha is 25.6 degrees. My beta is 42.9 degrees. And my C is 13.4. So again, we need to know what is the one of these other sides so I can get two sides in the included angle, right? So to do that again, here is my, I know what gamma is. I can figure gamma. That's the 180 minus the 25.6 minus the 42.9. And rather than doing this in my head, because I was having such a fun time doing that a minute ago, let's just go ahead and type that into the calculator. We get 111.5. All right, so now I can figure out A or B. I can figure out what A is or B is. It doesn't matter. I just need one of them, because as soon as I find one of them, I have two sides in the included angle, and I'm done. Ordinarily, from my rule of thumb I like to give you, I try to find the bigger side first, so let's just keep with that. Sine of 42.9 over the B is sine of 115 over the 13.4. So B will be 13.4 sine of 42.9 over sine of 111.5. So again, great job for the calculator. And we get 9.8038 for my B. Okay. All right, so we're almost done. The whole reason we had to find this is because I didn't have two sides with my included angle. Now I do. So the area will be 1/2 times that 9.8038. That number is in my calculator, so I can use it. 13.4 is the other side, and the angle that's in between those two sides is the 25.6. So we have 0.5 times the previous answer that's in my calculator, times the 13.4 times the sine of the 25.6. And again, that gives us 28. I'm going to leave the next problem in here as a practice problem because it's very, very similar to the one we just did. In the one we just did, we had to find gamma first because it was the missing angle. Notice in this one, alpha is the missing angle, so we'll find it first. Okay, and then you can figure out a side from there. As a matter of fact, since I have beta and B, once I have alpha, I can either figure out A or I can figure out C. It doesn't matter. Okay, so I'll leave that one for a practice problem for you. Let's look at this one, where we have three sides given to us. Pardon me. So we were given 89 on this side, 93 on this side, 65 on this side. Certainly that one looks like it's drawn to scale, doesn't it? All right. Again, we only need to figure out one angle. Once we figure out one angle, we're done because we have all sorts of pairs of adjacent sides here. I just need one of the angles. So, using my rule of thumb that I usually use, I will find this side that's this angle that's opposite. I'll find beta. So we'll use 93 squared, that's the side opposite, equals 65 squared plus 89 squared minus 2 times 65 times 89 times cosine of beta. That's using law of cosines, right? So remember, for law of cosines, the side that's on the left-hand side is opposite the angle that's on the right-hand side when you use the other two sides in the formula. So 93 squared is 8649. 65 squared is 4225, 89 squared is 7921. 2 times 65 times 89 is 1150. Sorry, 11570 cosine of beta. Let's isolate the cosine of beta. So we'll take that 8649, subtract off the 4225, and subtract off the 7921. We'll get a negative 3497 when we subtract the 4225 and the 7921 to the left-hand side. And we'll divide that by negative 11570. So beta will be the inverse cosine of that. And I can cancel out the two negative signs. And I get a beta of approximately what? Inverse cosine, 3497 divided by 11570 is 72.4074 degrees. Now that we found beta first, I have the two sides that are included. So our area will be 1/2 times 65 times 89 times the sine of that 72.4074. Which gives us what? We get 0.5 times 65 times 89 times the sine of the previous answer that's in my calculator. 2757.2166. Okay, there's actually another way we could have done this problem, and that's what's referred to as Heron's formula. I'm going to write this off to the side. Or sometimes you'll see it called Hero's formula, but Heron's formula is, I think, at this point more standard. Okay, so to use Heron's formula, the first thing we have to calculate is the semi-perimeter. Remember, perimeter is all the way around, so semi-perimeter is half of the way around, if you will. It's add the sides up and divide by 2. So in this case, the sides were what? A was 89, B was 93, and C was 65 over 2. So we do 89 plus 93 plus 65. We get 247 over 2, which is 123.5. All right, so Heron's formula says that the area, I don't even need to calculate an angle. I can take the square root of the semi-perimeter times the difference of the semi-perimeter and the other, or all three sides. So it's semi-perimeter times semi-perimeter minus A times semi-perimeter minus B times semi-perimeter minus C. Lots of letters there. But I know that the semi-perimeter is 123.5. A is 89. B is 93. And C was 65. If I type, not going to type in I'll type everything under the radical first. So the 123.5, and I'll multiply that by the 123.5 minus the 89 times that minus the 93 and times that minus the 65. I get 7,602,243.188. And if you do the square root of that, we better get the same answer as we got before. 2757.2166. 2757.2166. So again, if you have all three sides given to you, you can calculate the semi-perimeter and then use Heron's formula. It really doesn't matter which one you use. Okay, really does not matter. I'm not sure what just happened there. I don't know why that did that. See if I can make it go away. There we go. I think it was trying to load the typewriter, which I didn't want. All right. So let's see if we can do an example problem here. A rectangular dog pen. We're going to make a temporary fence from D to Y. We're going to keep the more energetic puppy away from older dogs. Okay. So the puppy's over here. We want it to play over here. They tell you that the OY is 12. They tell you that the DY is 31. And they tell you that this angle is 65 degrees. And it wants the area of the triangular puppy pen, so it wants the smaller triangle to the nearest tenth of a square foot. Well, this one's not too bad for us at all, right? Because they already tell us the pieces that we already know. This might have been a little bit more difficult to do had we not had or not given the pieces that were given. But this one's not hard to do because we already given two sides and its included angle. You could have also used Pythagorean theorem to find the third side and just do 1/2 base times height. That's also possible, but we'll use our new formula that we just discovered. 1/2 times 12 times 31 times sine of 65 degrees. We do that in this case. We would have times 31 times sine of 65, and we get 168.5732, and I know it said tenth, and I don't really care. Feet squared. All right, so that gives you an idea of an application. Let's see if we can do one more. And then I'm going to leave the rest for lecture for Monday. I will see what happens. I may just have to record lecture for Monday as well and have you watch it separately. We'll see what happens. But I want to do one more, and then I'll devote Monday to more application problems that are beyond triangles. If you notice that beyond this particular problem, you'll see things about rhombuses and other types of polygons. So we'll talk about those, like I said, for Mondays. But let's just do one more here. Slight variant on the problem. This one already tells you what the area is, and it said the triangle has two sides of 28 and 24 with an included obtuse angle. That's an important word here. And it wants us to find the measure of the obtuse angle. All right, so triangle has two sides, 28 and 24. It has an included angle that we're trying to find. Call it gamma, for lack of a better letter. I know the area is 280. Well, we know our formula for area is 1/2 AB sine of gamma. Again, the A, the B, the gamma, not the important parts. It's two sides and its included angle. Letters really don't matter as long as you have the two sides and the included angle. In this particular problem, again, they told you the area in this case was 280. We know that one of the sides is 28 and the other side is 24. So, if I isolate the sine of gamma, we get 280 divided by, and if I do the 24 times that, 1/2 times 28, I get 336. 336. I even said 336 and wrote the wrong thing. Okay, now we go along and do the inverse sine like we always do. So inverse sine of 280 divided by 336 is 56.4427. And we would be done except, remember back up at the beginning, I boxed it, now I'm going to circle it in red. In the beginning, we were told we wanted to find an obtuse angle. Last time I checked, 56 and change is not obtuse. How do we find the obtuse angle here? All right, well, we did this in the previous chapter, right? When we said when we were solving trig equations, we said that we had to sometimes go hunt for another solution. For when we had to do inverse sine, the way we hunted was to subtract it from pi. That's when we had everything in radians. This is in degrees, so the angle that we want is really 180 minus this 56.4427, which gives us the 123.5573. So this is the solution they're looking for the obtuse angle. None of this work was wrong. This work was all good. Just remember that inverse sine always gives us an angle between negative 90 degrees and 90 degrees. Negative pi over 2 and pi over 2. That's not obtuse. So since this was between 0 and 90, I had to go find the one between 90 and 180 by finding its supplement, by subtracting it from 180 degrees. All right, so like I said, I'm going to save the rest of these problems for a Monday lecture. Like I said, I may decide to just record it unless you listen to it, as opposed to trying to deal with the technological issues that we had today. It was really, really bad for you. I apologize again. It was not fun. I appreciate you being there, being on time. I sincerely appreciate it, and I appreciate with what all you're dealing with this time, trying to do all this stuff through e-learning. It's all new. It's all weird. And like I just said, I just wanted to let you know that I really do appreciate you taking the time out to come to class, and then having that mess happen today just was not conducive to learning. So like I said, I think what I'll probably do is just do a recording of the rest of these types of problems and let you watch them on your own, since we really are just dealing with the one formula. So there's not going to be any new formula. We're just going to talk about how to apply it in different situations. So until next time.